So when we first check what would be the losses and to what extent they will affect, or to what degree do the optical signals get distorted as they propagate down a fiber. So this is what we are going to see today. So signal attenuation or fiber loss it largely determines the maximum repeaterless separation between optical transmitter and receiver. So signal distortion cause that optical pulses to broaden as they travel along a fiber. Hello? Okay. Um, so this is a basic definition. So when the signal passes through it, the repeaterless transmission is determined by the attenuation. So next let us see the pictorial representation of it. Yeah. So if you have an optical fiber, so this you might have done as an experiment also, and even for this semester, you will have this experiment wherein you will have the optical fiber kit, so which will have the interface, like you have jumper pins to the board from where you will give the input from the function generator. So the input power typically will tell it in terms of amplitude. So you will be giving it from the function generator. So in a real world scenario, the power whatever you would like to impinge on the fiber, that you are going to give it over here. And a fiber will be optical fiber transmitter, and a receiver will be there. So you will be connecting it through those pins. So this is the optical fiber, and you will be verifying what is the output amplitude and hence the power. So when you calculate it, depending upon the length of the fiber, you will have the loss. So that is called as attenuation. Again, this loss is determined by the curvature of the fiber also. It is not that always you will have a linear connection from transmitter to receiver. So as you bend the fiber, how much is the loss? That is called as bending loss. Yeah, I am hearing that the voice is very feeble. Are you able to hear now properly? Okay, fine. Yeah. Mm. Now, uh, yeah, thanks, Vishnupriya. Now that we have the optical fiber, and this is the input power P of 0, and this is at the length L. What is the power after length L? So from the initial power, it will be degrading exponentially, and the order of or the proportionate of that is alpha p, which is called as attenuation constant. So you will be writing it in terms of in dB as well as in nepers. Okay, so that is this one. The parameter alpha p is called as the fiber attenuation coefficient. This is for per kilometer or nepers per kilometer or dB per kilometer. These are the three units in which the attenuation constant is represented. So in your lab, yeah, in your lab you will be verifying all these things. Yeah, and you may get a numerical problem also from this, maybe in your CIE or in quiz. So typically such a numerical problem for different length, you may be asked to calculate the attenuation and compare and write your inference. At times, you may be asked to just calculate the attenuation in terms of a particular unit. So the attenuation is like for dB per kilometer. So if you want to get it per kilometer, you have to divide it by length L. So in general, the definition is attenuation coefficient in dB will be given by 10 log to the base 10 of P of 0 by P of L, since your initial power will be higher than the final power. Okay. So when you are writing the gain, you will write final gain by initial gain. I mean final power by initial power. But here it will be the reverse. So it is 10 log to the base 10 of P naught by P of L. So this is for attenuation in dB. So if you want it for per kilometer, then you need to divide it by L. So if you have to convert it to Nepper, you should take it as multiply it by 4.343. So that is the idea. Yeah, before going into this, I think we have one thing I need to tell about. So in the last class, we have seen this diagram. A little more information I would like to add. Yeah, here. See the light propagation we talked about. So the core, you will have the inner glass tube is called as the core, and the outer one is called as the cladding, and you will have the refractive index difference. So which makes sure that total internal reflection takes place. Okay. So now, how much is the power launched inside this fiber, or how efficient it is to launch power? So that will be given by a parameter called numerical aperture. So that is your n1 square minus n2 square. So you will have this and the sign of theta naught is called as your no, the acceptance angle. At what angle, if you give the light wave inside the fiber, it will get launched completely to or confined to the core. So the sign of theta max is called as your, or sine theta c is called as your numerical aperture. So few questions may be asked, or numericals may be asked regarding that. Possibly you have it over here. One equation which I told you regarding the V number. Okay. In the last class. So there itself you can find it. Yeah. So here, so these expressions are important. Actually, this n1 square minus n2 square raised to the power of 1 by 2, it is called as numerical aperture. So that is in terms of your no, the refractive index. In terms of refractive index, in terms of acceptance angle, it is sine of theta max. And again you have something called your delta, sorry, root 2 delta will be your numerical aperture, and this n1 square minus n2 square, actually will be writing it as 1 minus n1 by n2. So that ratio is called as delta, or n1 square minus n2 square divided by either n1 square or n2 square. You will call it as the delta, that is the fractional difference in refractive indices. So in terms of the root 2 delta is your numerical aperture. So you may be asked some questions in terms of, like, given the core or cladding radius or wavelength, you will be asked for that. Again, A is the core radius. So these are few parameters which you need to remember. So now, understanding that this propagation is the initial one. So understanding this propagation, we are now going into the losses and distortions involved. Okay. So the audibility is fine now. Yeah, now it is okay. Okay, if you find any difficulty in audio, please put it in the chat box. Yeah. Did the same thing we are okay. Right. This is breaking, it seems. Hello? Is it okay now? Yeah, okay. So the ratio of P out by P in for 1 kilometer, so that's what you will try to write it in terms of P naught by P in. So if you want it for like per kilometer, if they ask, you need to divide it by that much of P. Just a moment. Amrita, is it working now? Okay, I hope the audibility is maintained now. So let me go to the next one. At times, you may be asked to uh, provide the value in another unit called dBm. So that is dB milliwatt. So this means how to write the power in milliwatt. So that is P naught uh, by P naught is there, right? So the initial whatever giving, you should consider it in terms of milliwatt or for 1 milliwatt. So that ratio is called as a dBm. So now we told that the loss there is attenuation. So that reduces the power. So what are the different causes or mechanisms by which this attenuation happens? So that is because of two things. One is called material absorption. The other one is called Rayleigh scattering. So now what is material absorption? So the core or the cladding, both they are made up of glass, predominantly silica. So these silica will absorb, that is the impurities added to it, they will absorb some energy. So but still we are using it because the absorption, material absorption is very less in this particular attenuation band. So the three mechanisms by which the attenuation takes place in optical fiber is, one is the impurities in the fiber material. So that is from transition metal ions or OH ions present in it. And second one is intrinsic absorption. So that is your electronic absorption or by virtue of the material itself. And as such, all the three are because of the virtue of the material. So one is by the impurities added to the material. The second one is by itself. In itself, it can absorb some energy. And third one is radiation defects. Uh, so this is actually the evolution of optical fiber. We will come across with this. So when we made the communication medium, when it is in silica, so even in the first generation itself, when it is silica, the communication actually improved. Then the law has been used to negligible levels at the wavelength of interest for optical communications, and Rayleigh scattering is a dominant component in all the three wavelengths. So that is what we are having it over here. I have not talked much about this because in the last class itself we have seen. We have three window where the attenuation will be very less. So that is your 800 nanometer or zero 0.8 micrometer. So similarly 1.2 and 1.5. Okay. So in these three regions, since the attenuation is less, means that your material absorption is less. But still, your Rayleigh scattering is yet another component which causes the attenuation. So how that occurs and what is it? Let us see that. Yeah. So in all these wavelengths, so this is attenuation loss. Now we are coming into the scattering loss. So what is actually scattering and how you differentiate between these absorption and scattering? So that is the second question. In attenuation, it is mainly determined by the length, not with respect to the size of the component, size of the impurities or the material itself. So it is not with respect to the size of the material and that of the light. So it is like the length over which you are transmitting the energy, and that energy, how it gets, keeps on reducing. But when it comes to scattering, like reflection. So what is the difference between reflection loss or refraction loss or scattering loss? When it is reflection, you will have two medium, and then as it passes through, it has to transmit to the second medium, but that will not happen. You will get back to the same medium itself. And the second process is refraction. So again, as it moves from one medium to the other medium, so it won't get directly transmitted. There will be a bending of ray, which is called as refraction. So for reflection or refraction, again, it is a refractive index of the medium cause, but not the size. But for scattering, it is the size of the impurity present or the size of the material with respect to the transmission wavelength. What happens is that as it is tiny, the reflection by very small or minute impurities, you will call it as a scattering. So small variation in material density or chemical composition or structural inhomogeneity will scatter light in other directions and absorb energy from guided optical wave. So this is the mechanism of scattering. Yeah. What is the difference between normal scattering and Rayleigh scattering? Is one of the question raised. Yeah, that's very obvious question. See, the normal scattering, it will just whenever it is comparable to your wavelength, you will call it as a scattering. So this particular Rayleigh scattering, it is found that this lambda power minus 4 of the order of minus 4 when it comes, you will or anything greater than 5 micrometer, you will call it as Rayleigh. Okay. So, but then again, it is not that precise, but generally, it comes from this Rayleigh Jeans law with this Hc by lambda. So, and it is proportionate to 10 lambda power minus 4. So, that is called Rayleigh scattering. And you will have two more scattering, Brownian scattering and all. So, as we move towards these scattering losses, you will find, you can easily understand what is the difference between each of them. So as of now, this is the simplest one, wherein the small material density variation will cause absorption of energy, and that is called as scattering, Rayleigh scattering. So again, this alpha scattering, this is called as your attenuation or the Rayleigh scattering parameter. So how much power loss will be there from this scattering? It is again determined by that 10 to the power of alpha L. Okay. So now this attenuation coefficient, this is no, you unmute.
Ma'am, the thing is, the first two questions did not have options, so I was trying to figure out. In that time, I couldn't answer it.
Okay, fine, no problem. Yeah.
Yes,
As
ma'am,
such,
but I was present, ma'am.
okay, fine, no problem. So
Yes,
it
ma'am.
was like okay. So the idea was to give it as a multiple choice, and I just wanted to know anybody had identified it. It is because Before I could give it as multiple choice, it has chosen the default short answer. So without knowing that I had given that poll answer, it appeared two questions. As such, I wanted to give some options over there. Anyway, never mind. This is not just like it's a quiz kind of thing. It's just I wanted to probe in between your understanding and how it works. Live of Beda. Now I hope it is getting shared.
Yes, ma'am.
Yeah, fine. Yeah. When you see this, probably I need to reduce the size. Yeah, here this gives you the graph. Along the x-axis is your photon energy, and you have the loss in dB and wavelength. So if you can see that, depending upon how much the source, how much emit. So that you can find out that so how the loss will be. Okay, and this is with respect to the wavelength, predominantly either at 0.8 or at 1.2 or 1.5. You need to check with this. So which laws you would like to uh, correct it. So if you see that your in infrared region, the absorption loss increases and your scattering loss is reduced. You have to actually find out a region or the attenuation window somewhere over here, wherein both your attenuation as well as scattering is a minimum. So that's how we will normally choose the particular window. Then coming into the a typical range, and intrinsic scattering and absorption is given in terms wavelength. Here it is only with respect to wavelength, the scattering and the absorption both have been shown. So if you can see that the intrinsic absorption, so the attenuation will keep on increasing, while the Rayleigh scattering will be reducing with respect to wavelength and thus in terms of frequency. Uh, so this is again yet another expression or another way of telling it. So different absorptions and waveguide imperfections. So we are going to talk about this waveguide imperfection or waveguide dispersion a little later. So there are various abnormalities or no the losses available. So the ultraviolet region absorb and how much will be a dispersion, how much will be the Rayleigh scattering, all with respect to wavelength it has been found, and you will be choosing. So the experimental value shows a curve like this. So you will try to choose where it is minimum. So which one you would like to keep in the most reduced form, or which one you want to optimize depending upon your source in which wavelength it operates, you will go for. So the silicon, so these are all some few informations. So normally they will not ask you for these parameter values, but like to understand this curve, you may require the knowledge of this. And local microscopic fluctuations in density is the cause for Rayleigh scattering. So this is what we talked about. Yeah. So yeah. So this is what the optimization here, what we talk about. So when you use a higher wavelength, the Rayleigh scattering will be less, but the material absorption of silica might increase. So you need to go for other materials. So that is the information we got. Next we are going for this bending loss. So this also you might have done it in your UG experiment itself. Yeah. It is not always our optical fiber will be used in a linear fashion. At times you need to bend them for various reasons while deploying. But this bending will lead to the leakage of power. So leakage of power in the sense the energy will be coupled from core to the cladding. So that results in loss. So the radius of curvature of the bend will be determining the amount of loss. Normally, if the radius is less, then your bending loss will be more. And again, with respect to wavelength, higher the wavelength, higher will be the bending loss. So the bending loss, so that is what? To keep the loss low, the bend should be in centimeter. That is, you should try not to bend it even if the radius should be more. So the smaller the radius means you are bending it more, and so there will be more loss. So the next part is the dispersion. So first we saw the absorption. So the next one what we saw is scattering. So the next one is dispersion. So for absorption, it is the material property. The impurities present in it. So that is the cause for absorption. So the second one is scattering. Scattering is determined by it is as such the reflection, but by the microscopic variation or microscopic variation of the density of the medium. Density of the medium in the sense it is not refractive index as such, but it is like the amount of impurities we can tell. So typically it is like the reflection from very microscopic impurities or materials or atoms present in that medium. Okay, so the third one or the third mechanism is called dispersion. So this is due to medium property, that is the refractive index of the medium. So phenomenon where the different components of the signals travel at different velocities in the fiber. So we already know that when you pass a light through the glass prism, dispersion takes place and the white light will get dispersed into its 7 constituent colors. So the same thing happens here. It is one white light with a particular wavelength or summation of wavelength. It passes through the glass. But the dispersion makes it, or how the dispersion as such occurs, because different wavelength will be traveling at different velocities. So that's why they are receiving at a different time. So the same thing happens here, and this is called as chromatic dispersion. So the chromatic dispersion refers to the phenomenon where different frequency components travel at different velocities in the fiber. Yeah. Dispersion leads to broadening of pulses. And pulses corresponds to the adjacent bits interfere with each other, and this is called intersymbol interference. So this is just like the normal RF propagation. So in RF propagation, what happens when the bandwidth of the channel is less, but more number of bits are transmitted through it, then you will find that one pulse will get overlapped with the other, and pulse broadening occurs or pulse narrowing occurs, which you will call it as intersymbol interference. So similar to that, here the dispersion leads to broadening of pulse and hence overlap, which is called as intersymbol interference. So this is given over here. See, you will have ones and zeros transmitted like this. Say a set of ones we are transmitting it through, or say 1 0 1 0 1 0. If you are trying to transmit, one will be transmitted with a narrow pulse, and 0, no pulse is transmitted as such. But then what happens? This one, it is getting So this is your sensing level. Now, so this one as such, it is getting broadened. And because of that, what happens to this 0? This pulse, it is getting narrowed down here. And, but still, you are able to resolve where the 1 is, at least from the peak. So, but then somewhere like if the number of bits increases or your sensing level is made higher, you can find that unresolvable broadening of the pulse. So this is the representation of your chromatic dispersion, pulse, and hence the pulse broadening. So this leads to a kind of dispersion called as waveguide dispersion. Waveguide dispersion occurs with multimode step index fiber, means you will have intermodal dispersion. Graded index fiber will have both intermodal and material dispersion. We are going to see about all these things one by one. See, first, what is material dispersion? It is due to the wavelength dependence of the refractive index of the fiber material. And waveguide dispersion is because of the wavelength dependence of mode propagation constant. So there are two things with this. Just like your material absorption, if you just consider the refractive index of the fiber material. So in chromatic dispersion, so what we have seen, it is like your material dispersion. So your ones and zeros will become unresolvable. Just the traveling speed of individual wavelength, that is the wavelength of 1 and wavelength of 0, they are getting, it is dependent upon that. But yeah, we will talk about this waveguide dispersion now. So I'll come back to this a little later to understand this. Yeah. So the second is the waveguide dispersion. So this means that the light energy of the mode, any particular mode that propagates. First thing is, you consider the multi-mode propagation over there. So the same light, when you transmit, the it will, one of the wavelength, it will transmit at a faster rate, the other one will transmit at a lower rate, because you will be transmitting one single frequency or wavelength, but it will get dispersed because of the refractive index of the medium. So that will lead to the chromatic dispersion. So the next one will be, you consider the that two modes are now traveling. That is, you have the chromatic dispersion. So one will move with one speed because of the refractive index of the medium. The other one will travel with another speed because of the wavelength to the refractive index. So that relation. Okay. Now, each of them, how much energy does it couple to the core and to the cladding is the second thing. So the mode propagates partly in the core and partly in the cladding. So trying to reduce the refractive index of the mode. So this will be resulting in dispersion called waveguide dispersion. So this will be determined by the propagation called beta 2. So here if you see, the mode propagation constant is called as beta 2. Beta 2, typically we say that because it is the second derivative of beta. So here, as you know, it is 2 pi by lambda. So this is called group dispersion parameter. So when you consider the ray propagation, then you will end up with chromatic dispersion. When you talk it in terms of waveguide propagation and mode, then you will come across with this waveguide dispersion parameter. So actually now the question comes, at a particular time, should I call it, or they the like will be, if there is a chromatic dispersion, will there be a waveguide dispersion, or they are like were complements of each other that we can represent one by the other and all. It is like they are two different things. So one can be explained by ray theory, the other one by the waveguide theory. But both the dispersions at any particular wavelength is possible. Yeah. So when beta 2, that is the second derivative, is greater than 0, we will say that the chromatic dispersion is normal. So that is pulse broadening will be less, or even if it is, still you can have a resolvable ones and zeros, or the resolvable pulse you can get when this beta 2 is greater than 0. But when beta 2 is less than 0, the chromatic dispersion will be anomalous. So this is what is the chromatic dispersion, I mean the waveguide dispersion, which comes under chromatic dispersion. So let us see that here. So this shows that this is a pulse. So each of the pulse, depending upon various colors, it shows that chromatic dispersion, which starts here. We are transmitting more than one color, it is getting launched, and depending upon the refractive index, they travel and reach the other end. So when n1 is greater than n2, the pulse what you are receiving will be like this. So here is a numerical. So that is, you have your n1 to be 1.5 and the fractional difference n1 minus n2 by n2 to be 0.01. So then how much will be the dispersion in the pulse width? So that is given by delta t, that is T max minus T min. So which component reaches earlier? So that is your T min. So this will be given by N1 into L by C. L is the length of the fiber. N1 by C will be the speed. So the maximum will be given by the variation N1 square by N2 times of L by C. So this you can try out by your own with the given values and you can understand. So for a variation of 0.01 and for L to be 1 kilometer, you will find almost 50 nanoseconds of pulse width broadening occurs. It becomes a pulse of, that is an impulse. Impulse means your duration is very small, approaching 0. So after traveling through 1 kilometer, will become a pulse of 50 nanoseconds duration. So this will affect in the number of bits that you will transmit. So that is the idea about this. I think the next topic will be this we talked about. Yeah, chirped Gaussian pulse. We are going for the non-linear dispersion. So I shall stop for today's class over here. So some few examples we have done. So I think 2 or 3 numerical problems I have provided in the presentation slide itself. Once I share, you try to follow it, and we shall take up them in our tutorial class also. And you find some a YouTube link over here. So these are all from NPTEL videos. You can go through these videos also to understand the concepts better. Okay. So with this, I shall